Just very quickly, just want to acknowledge the sponsors. We have a 5G Nokia smartphone that will be drawn at the end of the day today. You can see it's blending into my background there. And also want to acknowledge Google and the eSafety Commissioner, Yoga to Go, Tech2, and being there for some really great prices today. But look, without further ado, I'd love to introduce Alexander Lynch from Google. He's got great parents who gave him a really great first name. As you can imagine, I think that's a fabulous name. And he's here to tell us about the future trends in tech, which includes the exciting arena of quantum computing. Now, this is one of the technologies that is most likely to reshape our understanding of computers as we know it. And along with artificial intelligence, will bring us computing power from something out of a sci-fi movie. If you thought the last 50 years of computing were mind-blowing, wait till you see what the next couple of decades will bring. So a big thanks to Google as well for being a major sponsor. And over to you, Alex.
Well, thanks for having me here today. Can everyone hear me all right?
Yes.
Great. I really appreciate you taking the time to listen to me. And, like you said, we've gone through over the past decade some phenomenal changes in the way that we go about computing, AI being one that everyone has talked about, and I've talked about it a lot in the past as well. But there are big changes on the horizon. AI is rolling out across our economies, and we're seeing the benefits of that in medical treatment and diagnosis and those sorts of areas. But we have further revolutions on the horizon. The next big one I want to talk about is quantum computing, which we're just seeing emerging at the moment with some big scientific leaps. And I thought that would be an interesting topic for us to hear about today. Now, I'll just take time to share a presentation. Now, can everyone see that all right?
Yes.
Great. I wanted to talk about, starting with Australia, what is actually going on in the world today, to give some context to what we're talking about. Now, this picture is from the Australian of the Year Awards in 2018, where Malcolm Turnbull awarded Professor Michelle Simmons the Australian of the Year award. Now, she is considered arguably Australia's top research scientist when it comes to quantum technology. Her group and the quantum research teams that she worked with have been given almost $100 million by the government. The government is a co-investor in her quantum technology startup. Now, it may surprise you to know that Australia is one of the world leaders in this sort of technology. We have some of the most advanced research groups, to the extent that actually Google's quantum research head has come to Australia in the midst of COVID just this year to join Professor Simmons's quantum technology startup. We've seen this year also the CSIRO publish its quantum technology roadmap for Australia. To maintain our strength, they think that by 2040, our quantum technology industry could generate over $4 billion in revenue annually and support 16,000 new jobs across computing, sensing and measurement, communications, and other areas. This year, we've also seen the United States government publish a national strategic overview for quantum information science. And we're also seeing the analysis of quantum technology as a strategic factor in the geostrategic competition between the large powers like US and China. And part of this stems from the fact that we consider quantum computing to be potentially very powerful at factoring large numbers. And that's what we use to support encryption that protects our banking, our industrial secrets, our emails, our military networks. And if we solve, or if someone solves this problem first and is able to factor those large numbers, it could provide them with quite a decisive advantage. So you can see why there's a lot of scrutiny happening when it comes to quantum technology and quantum computing. But why is it so important? We know that it can have these computational effects, and you described them as something out of a sci-fi novel, and that's quite accurate. But why is it more powerful? We need to go back to the grounding in fundamental physics to actually understand why this technology is important and what it really means. Now, this is Professor Richard Feynman, a Nobel Prize-winning and very famous physicist that many of you will have heard of. And he said that nature isn't classical. And if you want to make a simulation of nature, you'd better make it quantum mechanical. We've seen physics experiments start to explore the problems of our understanding of basically the fundamental underpinnings of the reality that we perceive. Many of you may be familiar with this experiment. It's a fundamental experiment in quantum physics that showed the reality of this sort of these quantum theories, where they essentially shoot a photon through two slits in a wall or the experimental lab at once. And instead of what you might think, where you can draw a direct line between the light source and a place on the back wall behind the slit where the photon would have gone through, what you instead see is this stripe pattern, this waveform interference pattern, which is actually consistent with the photons acting as waves rather than particles. This means that in this situation, if we actually measure where the particle is, if we manage to measure the particle going through before it goes through those slits or even afterwards, we don't see that same behavior. We see what you might otherwise expect to see in a traditional sense, which is a single line on the wall. But if we don't measure it, then we see this wave formation, which means the particle exists, these particles, when you shoot it through, it exists in potentially multiple places at once to the extent that the probabilities interfere with one another. Now, this all sounds very strange on first blush. The fact that reality may actually exist in multiple states at once until observation collapses it into a form that we can perceive. And it's very interesting to look at the implications of that when it comes to some of the really, really fundamental physical properties that support our reality. One of them, which is close to my heart, is the ecosystem that we live in. The way that our planet essentially gets energy into our physical systems is by the sun. Plants capture that energy using a molecule called chlorophyll, and then that energy, we eat the plants, animals eat the plants, we eat the animals, it goes up the food chain. But fundamentally, the energy comes from the sun. Now, this energy capture is surprisingly efficient. You'd think a photon enters a leaf, it bounces around the inside of the leaf until it hits that part on the molecule that captures the energy. But every time it bounces around, if it doesn't perfectly hit that receptor every time, it should lose some of the energy. But instead, what we see is such an efficient capturing of the energy, it would have had to travel in essentially a straight line every time to the energy receptor. So what quantum scientists actually think happens is that the energy travels as a wave, and when that wave meets the energy receptor in the molecule, the energy collapses into a particle into that receptor. Again, very strange to think about how our reality fundamentally, in a way that directly supports our entire way of life, the entire system of life on our planet, is fundamentally reliant on quantum mechanical properties. And Professor Feynman's point was that how can we really understand the world that we live in unless we understand these quantum mechanical properties? People are investigating ways in which our mind may use these same sorts of energy efficiencies of using waveforms to transfer energy rather than particles to enable our consciousness. And they're investigating other areas, like the way that birds use to navigate when they're on those long migratory journeys. The internal compass that they have may in some way be reliant on the same sort of quantum effect. So it's a long roundabout way of me getting to the point that quantum computing can be thought of as a very powerful computer in one way, yes, and it does behave that way when it comes to calculating difficult numbers. It can be extremely powerful for the same energy efficiency compared to a standard computer. But one way of thinking about a quantum computer is thinking about it as being akin to a microscope, in that it allows us to simulate or understand a fundamentally more granular layer of our universe that we otherwise wouldn't have access to computing about. So the difference between a standard computer being a magnifying glass and a quantum computer being a microscope when it comes to understanding our world. We are just getting to the stage where we can really perform experiments with quantum computers that can not be performed in thousands and thousands of years, even by the most powerful supercomputer on the planet. Now that is called quantum supremacy. And Google's computer, the Sycamore system, quantum computing chips, achieved this quantum supremacy on a problem that a supercomputer would take 10,000 years to solve in October 2019. And it was a huge leap forward. And now Google's not alone in pursuing this technology. Google is one among many, including Michelle Simmons' team in Australia, including IBM and others. But we were the first to get to quantum supremacy and have subsequently been able to demonstrate that this technology can be used to better understand the world around us. This is the time frame we see when it comes to rolling out this sort of hardware. It's very, very difficult to maintain the coherence of quantum systems. And I'll go on to talk a little bit about why in a second, but you can see that there is a relatively near-term time frame. The next decade, we expect to have access to, or to be able to provide people access to solve quantum problems using our quantum computer. But if you look carefully at that little diagram on the bottom right-hand side of the screen, you'll see the word fridge in there, in that grey box. Now, this is really important to our work because we need to go back to think about that measurement problem that I was talking about when it came to that double slit experiment. When you measure a quantum probability, when you find that photon, the wave collapses into reality. So when we see it, it collapses the quantum properties, which means, and measurement in nature takes a very broad remit. Another particle bumping into it, for example, it counts as being measured to a certain extent by reality. And so if you have a very warm environment where there are lots of high energy particles bouncing around, there is more likely to be an interaction which collapses the quantum effect. So to make quantum computing work, it needs to be in an extremely cold environment. Heat is essentially agitation of particles. And if you take all of the energy out of it, it means that there aren't many particles bouncing around. The closer you can get it to absolute zero, the more reliable or the less interference there will be with your quantum calculations. Now, this is important in a number of ways. It's essentially been said that the difference between a $100 million, 10,000 qubit quantum computer and just a white noise machine is this ability to correct those errors when it comes to the quantum computing, because you can do a lot more. A standard computer consists of bits that can be flipped between 1 and 0. And error correction in traditional computing has been largely solved. In quantum computing, a particle you can essentially map the point on the particle, the information point, to a combination of the sort of latitude and the position on the sphere. And you can understand the complexity between that 1 and the 0 in a traditional computer. Being able to have a veritable infinite number of granular probabilities between that 1 and that 0 is what makes quantum computing so powerful for the same energy cost as a standard computer, and why the quantum computers can do things that standard computers just can't do. There are infinitely more positions that each individual 1 or 0 can be at, which means that you need far fewer of those particles to make the calculations, and therefore a lot less energy, but they are very unstable. Any kind of derivation from that point that you're trying to measure essentially ruins the calculation that you're trying to do. But we are having, under these very specific conditions with very small number of qubits, able to perform quite spectacular calculations. And I talked earlier about thinking of quantum computing as a microscope on reality. That's because we can really simulate at a fundamental level some of these problems that we need, that have quantum properties that we need a quantum computer to solve. And we can map out what undiscovered chemical molecules might be out there. We can solve mathematical problems like the traveling salesman problem. What is the optimal route in a very complex situation between different areas? These optimization problems. And we are only just starting on that journey. You can see here that computational volume of quantum computing is expected to double every few years, and the computing power required to keep up with classical computing is exponential with the volume. We simply can't, with our classical computing frameworks, solve those very, very complicated problems that quantum computers can solve, let alone simulate quantum properties. And so that's why this technology will become so important to us over the coming years. Even in traditional computing or classical computing, the computational power required to train the artificial intelligence algorithms that we're starting to see rolled out across more and more of the economy over time is increasing at a logarithmic rate, which is essentially like a hockey stick graph. Like, for the more complex the artificial intelligence problem to solve, the more computational power you need. And that means more energy, it means larger data centers, and it's simply not sustainable to go on doing that over time, given that we'd like to roll out these technologies across our whole economies and societies in the same way that electricity has transformed our societies, which means we need to find ways to do this computation more efficiently. And that's where quantum computing comes in. Some of the things that it might be useful for, some of the things that we might need to think about when it comes to our societies, is having autonomous vehicles that can perform the calculations they need without having to be connected to the cloud. Obviously, connectivity may become an issue, and that presents safety issues for driverless cars. And we can make them smarter and more capable if they're able to perform computations more efficiently. We can, as I said, train our AI algorithms very fast. We can assess huge, complex data sets very rapidly in a way that you simply can't do with our standard computation. Materials science, we can identify superconducting materials, which means low loss power transmission. We can change the nature of the materials that we use and the energy sources that we derive by having these advanced simulations that take into account quantum mechanical properties. We can design using chemical investigations or synthetic chemistry investigations, industrial catalysts to break down plastics and reduce our environmental footprint here, make better fertilizers for our plants, and better methods of analysis in medicine and that very high-end chemistry and deep science, where breakthroughs will start to layer up to advance our medicine, our energy, and other areas of the economy and society. But it does present challenges for us as a society, as governments, and as companies that are trying to work in this area. There's a lot of concern about artificial intelligence when it comes to black boxes, that it's very hard to understand what's going on inside a neural network. How did a certain set of inputs get to a certain set of outputs? In the same way that it's very difficult for us to describe how we might have come to a conclusion ourselves in terms of the way that our brain has processed our experiences and lent us to make a decision based on those. The more complex the problem, the harder it is to describe how you got from A to B. Intuition, for example, we use intuition to describe a sort of our fundamental belief in something, but we can't describe why we hold that belief or how we got to that conclusion necessarily. It's the same with AI. This is really presenting problems for policymakers who would like to know why a certain person received a certain result on there in a situation where an AI is used to determine a credit decision, for example, and that sort of transparency is an active research problem in terms of how we build that into our systems, so that we can help to provide people justice when it comes to the decisions that are being made about them, which is hugely important. With quantum computing, it's another level of this problem entirely. It's not simply the complexity, it is that when you observe a quantum property, it collapses, it no longer exists in the way that it did. And so we simply can't observe the inner workings of a quantum computer without destroying the quantum computer. This means this black box problem goes from a very difficult, not intractable computer science problem to a problem of basic physical properties. And so we will have to figure out how we can develop ways of better understanding or auditing results between the inputs and the outputs, rather than having to rely on understanding how the computations are taking place inside the machine itself, in the same way that we're grappling with this problem in AI. People often, after these talks, ask me where they can go to start. And I don't recommend quantum computing for babies for people on the call, but I have got this book for my child. Chris Ferry, one of the authors, is a quantum technology specialist at the University of Technology in Sydney, and produces this book and a whole series of other books about science for little kids. I'm a father myself. I have a 2-year-old and a 3-month-old now, and my 2-year-old loves these books and knows this one on quantum computing to the extent that he can recite it to himself back to front. And so there are very smart, Ivy League or high-end university trained scientists working on these problems. But when this technology becomes widespread, the people who have to work with it and understand it will be, our children, the next generation. And so part of what I see my responsibility to be, and what I would hope people in the audience think as well, is that we have a responsibility to help the next generation as they're growing and learning to focus on things that are going to be relevant to them in their lives. And sometimes that means a book, Quantum Computing for Babies, and making sure that we're spending that time and showing them what might be important. I hope that's been an interesting overview of the state of quantum science at the moment, and potentially what the possibilities will be, and given you some kinds of insight. I'd love to take any questions if anyone has in the meantime. Thank you. And it doesn't have to be about the presentation, but technology or Google more broadly as well.
Well, I have a question to start with. So, Alex, obviously people think of a computer today as their desktop or their laptop, and clearly a computer that is quantum powered, that is going to be completely different to the sort of computers we have today. I mean, what will that sort of quantum computer look like in 20 years? Will it be something that wirelessly interfaces with our brains and sort of augments reality in the way that the Matrix may have depicted? I mean, will we still have laptops or wearable computers in that time, or is the whole way that we interact with computers going to change as radically as the mouse and touch changed it for people who were born in the 1800s and could never have imagined of such a thing?
Yeah, that's a great question. I think it's not even necessarily specifically to do with quantum computing, but I think unequivocally the answer will be yes. That we have this idea of something called environmental or ubiquitous computing, where computers will operate or be interfaced with in ways that are more naturally human. Like the keyboard, we're used to it because it was the way we've done things for a long time. Before that was punch cards. Obviously, those aren't very human ways to interact with things. And what we're likely to see in the future, and we're seeing that the very first tentative steps towards that now in smart home devices and the like. What we're likely to see, we've got serious cybersecurity and privacy problems to solve in the meantime. Is computing where you can walk around and talk to the computer if you need to. It understands what you want personally. You can use gestures to communicate, or you can just use your voice, and that the systems that we have in the future will be a lot better at interpreting what your intent is and providing relevant feedback on that intent, rather than us having to. I don't know if all of you remember, probably almost certainly do, where you had to actually type Boolean searches into Google, and now you can, as in, I want this and that, and have some brackets in there to try to get the information back that you wanted. And now you can type in a very natural language string, and it can interpret it. Like, each of these is a slight step down that road, but we can expect computers to be a lot more easy and more human to interact with in the future.
Yeah, I mean, it's certainly the case that smart speakers, the Google Home speaker and the Alexas and the Siris can, take our spoken requests, and their ability to understand what we say has jumped tremendously over the past few years. And that is sort of the natural computing, natural user interface that we're going to go down. Will quantum computing enable us to sort of think without having to say anything at all, or, and just think of something and access the internet and all the information that way, just by pure thought?
I mean, Elon Musk would probably say yes, but I'm not sure. I think that requires a whole new level of technology and social comfort with that sort of technology. If you're thinking about how something might interact with your mind, it could be something that is implanted in there, or it could be some kind of sensor array which interprets what the sort of patterns of energy that are present inside your brain and translates that into intent for the computer. But that is, if it's going to happen at all, and that's by no means a sure thing. It's years away, and certainly not a practical physical problem right now.
Yeah. I mean, we do hear about developments for people who are physically impaired, where they can think to turn lights on. Yep. And supposedly I've heard of, I don't know if it's true or not, but they've been able to, type words on a screen. But that, of course, is extremely basic compared to what's going to come. It's like comparing a typewriter to using Google Docs in your browser and being able to have a lot of people collaborate at the same time.
Yeah, but you can see the very first inklings of all of these things happening. Like you said, you can see, particularly focused on people who have who lack the ability to interface with the computer in the way that many of us take for granted. Those are problems that people are currently working on, and it may seem like child's play now, but in 2 decades, 3 decades, our capabilities will be far in advance of where they are. We just have to our burden as a society is to make sure that we're steering in the right direction, we're hedging off all of the bad use cases, and we're making sure that we're focusing on the things that matter, that deliver, really good outcomes for human beings and let us live our lives in a way that we want to, rather than forcing us to live our lives in the way that machines would rather interact.
On one of the slides, I saw that you said that quantum computing would be great in helping us to achieve nuclear fusion, which of course is a tabletop energy system that uses the same sort of technology the sun is using to create energy, but can be done in a way that creates no waste. And I mean, we had the cold fusion theories of the 80s and 90s that didn't quite pan out, but augmented thinking and the ability for humans to achieve far greater things is coming in our future with quantum computing. And that's going to, that's going to take, I mean, for the sort of geometric progression of the evolution of humanity thus far. I mean, once we get quantum computing, it's going to go like that.
We would hope, but we're still constrained by the problems that we want to solve, right? And that's a lot of what I'm thinking about at the moment, and I'm trying to work with Australian government and companies about is how would you want to use this technology? What could you do? What would it be useful for? What sorts of problems are on your mind and could help solve this? Because it really is about, we're still, regardless of the power of our computation, we're still limited by our human creativity and ingenuity, at least for the time being, and that is still how we prioritize the way that we think, our culture and our cultures variously across the globe. And this is why diversity of thought is so important, and having people with different life skills, with different backgrounds, different ages, working on these problems, or making sure that they are aware of and thinking about these things is hugely important. Because it's one thing to have a bunch of tech bros in Silicon Valley and hoodies thinking about something. They have a very narrow worldview, and this is why we need a lot of people across societies thinking about how these things might be used.
Sam, do you have a question?
Yeah, I've got a couple of questions from the audience here. Teresa Corbin asked, given how cold the environment needs to be for qubit, and like you've just been discussing, what does it look like in the future? Will we all have quantum computers in the future, or only big businesses?
So and you can see this happening today outside the quantum sphere, right? Most of our technology is delivered via cloud computing. All of our Google searching, our emails and whatnot are all processed on vast football field sized data centers stacked with supercomputers and processing power, and delivered via huge telecommunications networks and subsea cables and 5G infrastructure and all of these sorts of things. Some of that will continue. We are doing more now to bring the processing power required by things like basic AI down so it can be processed on device, and we call it edge computing. So there's probably going to be a bit of a balance between really high-end supercomputing and quantum computing hosted in huge facilities where you can really cool them down, although we're trying to work on error correction that will allow us to do it in a less artificial environment, so to speak. But there will have to be balance there. Exactly, less fridges, because they take energy, and fundamentally, we need to be very conscious about the burden we're putting on our environment as we move into a world of more and more computing.
I think there's some maps out there with the size of energy taken by a lot of those, not just the data centers, but the exploratory computer centers. So
completely. And we've actually rolled out AI across our data center network that actually manages the energy consumption now, and it's basically making sure that it gets as least hot as possible. So there's a water and cooling element to it. And for us, it's a business cost. Electricity is a big cost, but it also has an environmental effect. And so that has allowed us to reduce our data center energy consumption by 20% across the board by letting it almost manage itself, which is pretty incredible for us as a business, but also speaks to how, as we can apply these computational systems to more complex problems, we might be able to find those efficiencies that actually help us, even as we become more capable, to manage our consumption of the world's resources better.
And use it in other areas. There's one last question for you, Alex. Margie Parsons said, thank you very much. Very interesting. She would benefit from reading an article such as Quantum Computing for Beginners as a follow-up. Do you have any suggestions?
Sure, I can certainly share a whole lot of things that might be useful for people to read.
Yeah, that'd be fantastic. And we'll post those on our conference website in the News to Inspire section there. So please do go back to that conference website. That would be fantastic.
Great.
Alex, thank you so much for your time today to go through quantum computing. It's a big subject and 30 minutes isn't a lot of time to cover it off.
We have to make do with what we have.
Yes. But we really appreciate that. We really appreciate Google as one of our major sponsors. You've been a big partner of ASCA for many years now.